All right, how's it going, everybody? We are here for our second section of week 10. Today we're going to talk about section 8.1. We just wrapped up chapter 7 with our previous video, and we're now going to move on to like sort of a smattering of other topics that are going to be associated with this class here. We're going to hit a couple sections in chapter 8, a couple sections in chapter 9, and a couple sections, I believe, in chapter 10 as well as we kind of we're obviously in the second half of the semester here. We got kind of 5 more regular weeks of content left to go, plus finals week is week 16. So we're on to sort of the last third of the class right here. So section 7.8, in my opinion, is very, very challenging. And I even honestly skipped some of the hardest problems that are in section 7.8. That stuff can get pretty tough out there. You're going to see today that section 8.1 is going to be quite a bit friendlier to you here. In fact, what you're going to see is that most of the topics today that we're discussing we've actually already covered in this class, and it's really just kind of one special calculation that's not difficult at all that we just want to incorporate into this idea here of solving right triangles. In general, in chapter 8, the 3 sections that we're going to cover in chapter 8 are going to deal with solving triangles. To solve a triangle is to identify the 3 side lengths and the 3 angles associated with the triangle, interior angles, those angles on the inside there. A thing that's kind of good, a perspective thing for you to take a moment and recognize is that so far in this entire class, we're on week 10 right now, and we have only talked about right triangles. Isn't that kind of insane that we have 10 weeks worth of stuff to say about right triangle trigonometry? So finally, next week in sections 8.2 and 8.3, we're going to talk about the law of sines and the law of cosines. These are going to be two formulas effectively that are going to give us ways to solve non-right triangles. So we're going to finally talk about triangles that don't include a right angle for the first time in this class next week, week 11, sections 8.2 and 8.3. Today is the one section of chapter 8 that still just involves right triangles, so nothing's really going to blow your mind too much here today. And 8.2 and 8.3 won't really be terribly difficult, but they'll certainly be a little bit more challenging than today. But I think that honestly today is relatively easy here. So our goal in chapter 8 is to be able to solve all triangles that are solvable. If we have enough information, we want to get all the information. 3 sides, 3 angles. That's what we would like to know everything about any given triangle. So again, our definition here says solving an equation, I feel like, is something that people are a little bit more inherently comfortable with. If I say solve an equation, what that means is determine all values that the variable in the equation could possibly take on to make the equation true. Solving a triangle is something that I feel like oftentimes people are like, wait, what do you mean solve a triangle? To solve a triangle is to identify all 6 of its relevant measurements. 3 angles, 3 side lengths. So today is the easy ones, right triangles. We'll get our slightly tougher cases with non-right triangles in the next 2 sections here. So what we want to do is just remind ourselves, what are the equations that are going to relate side lengths to each other and interior angles to each other? So kind of all we got to really remember for ourselves here is that in general, we can picture our general right triangle here. And importantly, I want to start doing some labeling things that are going to be important labels for you guys to be consistent with in the next couple of sections right here. We're still talking right triangle today, but in the next 2 sections, we're going to talk about non-right triangles here. So a very typical thing for us to do here is to talk about side lengths, legs being A and B. Hypotenuse is always C. And an important thing is that it's very, very common for lowercase letters to be used as the side lengths. And this is one of those things, who really cares what kind of variable descriptions we give for the side lengths and the angles? I'm just saying this is something that's consistently done enough across most mathematicians that people assume that everybody's on board with this general structure that people have come up with for like naming these types of things. Similarly, it is common to use either Greek letters or capital letters to indicate angles. So I would call this guy capital A. And notice, I'm not just arbitrarily selecting these. Angle A, right there, is the angle that is opposite of side length A. Opposite of side length B should be angle B. And therefore, it should always be the case, since A and B are kind of like arbitrarily selected right there, it doesn't matter which of the 2 legs you call A and which one you call B. C is always going to be our hypotenuse. Therefore, capital C is always going to be our 90-degree angle right there. And by the way, again, I said that another common thing to do is to use Greek letters instead. So it might be the case that we're calling this alpha, beta, and gamma there for our 3 Greek letters here associated with those ones. I'm probably going to use capitals just because they're a little bit easier out here. But anyway, the point is legs that aren't the hypotenuse are lowercase a and b. The hypotenuse is lowercase c. The angle names correspond to the side length names that they are always matching with the opposites right there. And the reason why this is important is because I want to be able to describe a triangle to you without having to draw it. And so I might give you, and as we're going to see in some of our upcoming problems right here, things like solve the triangle with A being 40 degrees and B being 2. I don't need to be able to draw you the triangle for you to be able to interpret exactly where the measurements of 2 and 40 degrees go relative to one another. And that actually matters. Otherwise, we're not solving the same triangle as each other right there. So recognize here that this naming convention, the consistency that we want to maintain right here, is important so that we can kind of do some of these problems without necessarily having to draw a picture every time. Right? So, well, though, I'm still going to draw a picture every time, but I might not draw a picture to present my information to you. You should be able to interpret what I mean if I tell you A's, B's, C's, uppercase, lowercase, stuff like that. So what equations do we have to relate these things? Well, we know that to relate our side lengths here, we have the statement a squared plus b squared equals c squared. That's our Pythagorean theorem right there. The other thing that's really important for us to know, so this is our side length or relationships. For our angle relationships, you know that alpha, or sorry, I'm going to do my capitals here instead of my Greek letters. I was just starting to write my, and I wrote gamma for alpha anyway. So it should also be the case that a plus b plus c equals 180, right? Interior angles of a triangle will always sum to 180 degrees. And for right triangles, it's always going to be the case that C, sorry, I'm trying to write and talk at the same time, that C is going to be 90 degrees, always in a right triangle. So in right triangles, you get the even, oh my gosh, I can't write right now. In right triangles, you get the even easier statement to relate your two angles, which is really just the sum of the other two angles is 90. Get out of here. So these are kind of my two guiding statements for myself right there. And we already knew both these things, right? This is nothing new right here. Really, the most important thing maybe is just for you to remind yourself A, B, and C and capital A, B, and C are always how we measure side lengths and angle lengths, and they're not just mixed and matched out there. A is opposite of A, B is opposite of B, C is opposite of C. That's how we maintain consistency here. So what we would like to be able to do is to solve all possible right triangles. And so what I think a reasonable thing to do would be to say, what if we knew 0 side lengths? What if we knew 1 side length? What if we knew 2 side lengths? What if we knew all 3 side lengths? This is in effect going to help us cover all possible scenarios associated with right triangles right here. So this is just one way that we can come at making sure we see a little bit of everything. So first example here is, can we solve this triangle right here, which has a 90-degree angle, a 20-degree angle, and a 70-degree angle? And the thing that you should recognize right away in this scenario here, zoom tight. So, is that in this case right here, we're not given any side length information. And what you should remind yourself here is that this is exactly kind of where we came up with all of our definitions for sine, cosine, tangent, secant, cosecant, cotangent, is that these are ratios of side lengths and that those are consistent with any degree measurement because our triangles, if we only know the angles, could be huge or they could be tiny. And so kind of recognize that this could be of any size. Right, this could be our 20, and this could be our 70. Or we could be getting some massive triangle out there, right? That's a 20, 70, 90. So, could be any size. So this is basically our way of saying, never mind, you can't do it. So our first example of the day is an example to say, if we don't know at least one side length, you straight up can't do it. So our 0 side lengths known, all of these triangles are what we would say are similar to one another. They all have the same angle measurements, but we could scale it up and scale it down and maintain the same ratios. So in all of these cases right here, you could take the sine of 20 degrees and you're going to get the same thing for all 3 triangles. The tangent of 70 degrees, whatever you want to do here, all the trig ratios will be maintained. But that scaling could go any direction right there. So we have to know at least one side length to ever solve any triangle. That's kind of a general statement that'll be true for both our right and our excuse me, for our right and our non-right triangles that we'll cover in the next couple sections. So we can't solve, basically, is our statement that we're looking to make right there. So if zero side lengths are known, then you can't do anything. So let's move on now to one that we actually can do. If one side length is known, what I'd like to do is solve the triangle with A being 40 degrees and B being 2 degrees. Now, what I'm thinking to myself is, let's go ahead and set up just a way to report our answers before we even start this thing right here. Then we'll draw a picture, then we'll do the math, then we'll fill out the rest of what we found here. So what I'm thinking to myself is, I know that our responsibility if we're solving a triangle is to come up with 3 side lengths as well as 3 angles. So I'm just going to lay those out for myself right here. We already know that A is 40 degrees and that B is 2. So all this stuff that's given to us there is in black. Let's go ahead and draw a triangle that has this set up right now, and then we'll kind of work towards the pieces of information that we can get access to here. So here's a generic right triangle. Certainly the case that I don't ever expect that these are actually drawn properly with the proportions right here. Like, I'm not necessarily worried about getting something that actually looks like a 40-degree angle in here. But kind of right away, one of the things I am thinking is, if one of our angles is 40 degrees and one of them is 90 degrees, then what must be the remaining angle? Well, what we just discussed up above is that the sum of the 2 non-90 degree angles should be also 90 degrees to get us to a total of 180. So if A is 40 here, then I know that A plus B is 90. So 40 plus B is 90. And so B, therefore, must be 50 degrees. So before I even start labeling things on a triangle, I'm noticing that since A is 40, and that's the smaller of my 2 angles, I'm going to go ahead and place that guy over here. This is my 40-degree angle. Therefore, this is going to be my B. This is my 50-degree angle. And based on that, I think I can say this is going to be my lowercase a, since it is opposite capital A. This is going to be my lowercase b, since it is opposite capital B. And we know that that b is going to be 2 right there. Right? So what I actually think I want to do, well, I'm going to use some other colors that are out here. So what we know is we know all 3 angles already at this point, and we know that lowercase b is 2. So I'm going to switch to purple here and indicate that the purple ones are what we've solved for. And I guess it should be the case that the 90 degree is given in black, because that was officially given to us and that it was a right triangle right here. So it looks like what our job is now is to solve for A and for C. Those are the 2 pieces of information that we still would like to know. So here's the thing that I'm thinking to myself. I should be able to come up with several different ways to come at these, because we have lots of different trig functions that can help us relate these. So there's lots of ways to solve for A here. So I'm going to say that. Lots of ways to solve for A. And they're all going to give us the same answer. But I'm going to write out like a whole bunch of different equations that I could possibly set up to show you all the different choices that you have. There's so many different choices that we have to solve for A here. So what I'm thinking to myself is this. Since B is 2, this is the side length that I know. So this is the side length that I should use to help me determine what A is going to be. If I want to think about this value of 2, I'm also probably going to want some of this angle measurement to help me figure out how is this side length of 2 related to this unknown side length of A based on an angle that's been given to us. So here's some of the statements I'm thinking. Relative to the angle A, capital A, B is adjacent, and lowercase a is opposite. So therefore, it sounds to me like if I talked about the tangent of 40, tangent is opposite over adjacent. In fact, I'm going to back up one step here. And I'm going to write this in general in terms of our generic letters here. That tangent of A is opposite over adjacent. And therefore, that means to me that tangent of 40 is going to be our unknown A over 2, and therefore 2 tan 40 should be A. That's one way I could have come at that. Another thing I could have noticed right here is that I have this angle B available to me as well. I know that B is 50. I'm noticing that the known side length of 2 is opposite of B, and when I think opposite here and I want to solve for A, I'm thinking opposite and adjacent right there. It looks like another thing I could set up would be that tangent of B Well, relative to angle capital B, opposite is B over adjacent is A. So notice that by switching which of the angles we're choosing, we're switching the fraction that this tangent function is associated with. So it should be also the case that tangent of 50 is equal to 2 over A. Now notice here this is a slightly less comfortable situation for me to land in right here because it's not like I can just do one math step of over here we just multiplied by 2 and we had A left alone. Here I don't quite get that. So I'm thinking to myself, I want to multiply both sides by A. And now if I divide both sides by tangent of 50, we'll have our answer here. All right? So maybe that's not quite lots of ways. Maybe I exaggerated here, but I think I can say several ways. And so these are two different expressions that should be giving us a value for A here. So I'm going to go to my calculator and get a value for A. My calculator right now is just Desmos, and that's fine. So I'm going to do 2 tan 40, and I'm going to verify with myself. Sorry. So Desmos is going to be, by the way, Desmos is always in radian mode. So I need to go ahead and multiply this guy by pi over 180 at 40 degrees to get my actual tangent value that I'm interested in. Similarly, I could also do 2 divided by tangent of 50 times pi over 180. And I'm getting the exact same thing for both of these guys here. In fact, you can still, yep, there it is right there. You can still see this in my calculations that I'm doing right here. Again, Desmos always stays in radian mode. So if you want to do 40 degrees, I'm actually converting 40 degrees into radians by multiplying it by pi over 180. And you should see here we are getting the exact same decimal expansion for this 2 tangent of 40 degrees or 2 divided by tangent of 50 degrees. So I'm going to call this 1.678 is a good round to 3 decimal places there, 1.678. So it looks like we've solved for A. We got 1.678. So now to solve for C, we've also got some more choices. You should now notice that since we know lowercase a and lowercase b, we can use the Pythagorean theorem to solve for C. Or set up more trig statements. You got options here. And let's just do both and show that they're going to be the same. So one thing I could do here, and again, I'm doing overkill work here. I'm like doing double the work I need to for this problem, but that's just to show you guys all of our options that we could use to kind of make this guy happen here. And so by the way, we have found that A is going to be this 1.678. So it looks to me like I could say something now like 2 squared plus 1.678 squared is going to be equal to C squared. And again, if I go to my calculator and I check out this guy, we should be getting square root of 2 squared plus 1.678 squared. And that will be giving me C to B. And I'm going to go pop over to Desmos here, square root of 2 squared, which is 4, plus 1.678 squared. And I'm getting 2.611 if I round this to 3 decimal places, 2.611. So it looks like we have, a second. Oh, okay, sorry, I was talking myself out of that for a second. There we go. 2.611 seems to be my C value here. So I've solved for C that way. Another way that we could have totally done this instead is to say, listen, we know both of our side lengths by now, so I could maybe set up, in fact, there's now like 4 different trig statements I think I could easily set up here. I'm noticing things like relative to angle A, B is adjacent and C is hypotenuse. Adjacent over hypotenuse sounds like my cosine statements. Cosine is adjacent over hypotenuse. So I'm thinking things like cosine of A should be equal to 2, Let me draw my generics right here. I'm not going to work this one all the way out, but you can, and you can verify for yourself in your calculator. This will work out to be the same thing. So in this drawing here, cosine of angle A, cosine is adjacent over hypotenuse, that's B over C. Alternatively, I could set up statements like sine of angle B, because sine is opposite over hypotenuse, so that would give me a 2 over C for the sine of B here as well. So it looks like we could make statements like cosine of, and what was capital A, 40 degrees. That should be 2 over C, or sine of 50 is 2 over C. Notice these are both equal to 2 over C. Remember that this is actually just our complementary angle theorem that we've come up with, in fact, 2 different times this semester. All right, there's our complementary angle theorem here. If you take the opposite angle out of 90 degrees, then you can switch between sine and cosine. That's exactly what we've got right here. In this case, cosine of 40, so theta is 40. It's equal to sine of 90 minus 40, which is sine of 50 right there. So these are 2 other statements. Or we could have done something like this guy right here, and you can solve either of these equations for C, just doing a little bit of algebra like we did here before. So kind of the point here with this guy is this was not really that hard. We got our final solution right here, and there was lots of options that we could have taken. This is basically saying set up any trig ratio you can that involves one piece of known information and one piece of unknown information relative to a known angle, and we're good to go right here. You should also notice that as soon as you're given one angle, the very first thing I did was solved for the other angle that we didn't know, because that's really easy. It's just a little simple subtraction problem. Once we know all of our angles, then we can do any trig function from any of those angles, and we just want to make sure, as we did right here, that we incorporate one known angle with one unknown angle so that we can solve for the unknown angle right there. So it looks like we have solved this triangle right here. We did have to use our calculator to solve for some of these, to get some decimal estimates for this thing right here. Remember that your TI calculator has radian mode and degree mode. Remember that Desmos is always in radian mode, so you need to convert things into radians by multiplying by your pi over 180 if you're ever going to use Desmos for these types of calculations if they're in degrees. Okay, so let's do another here. If 2 side lengths are known, let's go ahead and solve the triangle with A being equal to 2 and B being equal to 3. So I'm noticing here right away that I don't have any angle information for myself, right? Which makes this quite a bit different than the previous problem. So I'm going to immediately go into drawing my right triangle right here. A is 2 and B is 3. So I think that I'm going to let my short side here be the shorter of the 2 and my long side be the longer of the 2. But you guys have seen, I pretty much draw the same triangle regardless of the measurements that I'm giving, unless it's something extreme out there. So I'm never worried about your triangles truly being representative of the actual measures being given, as long as things are within, as long as it's readable out there, right? So it looks like we're missing C, and it looks like we don't know any of A or B, and we at least know capital C, but we always know that guy, right? So again, I'm going to set up my little table of the information associated with this triangle, and state what I currently know so that we can figure out exactly what is it we want to know. We know that A is 2, we know that B is 3, we know that capital C is 90 degrees. So our interesting dilemma with this one here is we weren't given any angle information. So what are we going to do? Well, if I wanted to find an angle, let's make a statement that involves some sort of angle. I think that okay, so I guess a couple different things here. One, we could use the Pythagorean theorem to solve for C right now. We can do that. Maybe I guess we should. But it's not going to help us get our angles, right? So these are kind of 2 separated issues for us. One, solving for the final side length, pretty straightforward. Solving for the angles, this is our new one here today that we haven't talked about. So let's say solving for C, pretty easy. A squared plus B squared equals C squared. So the good thing about knowing 2 sides of a right triangle is you're guaranteed to be able to use the Pythagorean theorem to solve for the third. 2 squared plus 3 squared equals C squared. That's 4 plus 9 equals c squared. It looks like c is going to be the square root of 13. And in fact, and I'm going to, by the way, I'm going to say this right now, if it's possible for you to get any values without going to your calculator, then that is what is preferred. I would rather see a square root of 13 if we can get something exact like that rather than decimal. It's just that over here we don't have an exact way to write things like tangent of 40. We're never going to come up with an exact representation for that. I shouldn't say never, but would be really, really, really difficult with me using a whole bunch of different identities to work around to make that happen. That's not really a reasonable thing to do. This is very exactly square root of 13. It's a simple expression right there, so that's a good expression for us to use for C. So it's solving for capital A. That's going to be a bit, it's not really that hard, but this is our new thing for the day. This is the one thing we haven't done before that now we're capable of doing since we've covered chapter 7. Further, I want to say, if we can find either angle A or angle B, we can easily just subtract that angle from 90 to get the other one. So we really only have to do work to find one more. Then the fact that our two smaller angles are going to sum to 90 is going to get us the other one basically for free right there. So let's say solving, get it black here. If we can find one. If we can find one, then a plus b equals 90 gets us the other one, right? So all I need to do is do the work to get one. So again, this is like our new topic of the day right here. The previous problem that we did involved no math that you haven't seen before. This was stuff that we did back here in chapter 6. We're just kind of refreshing ourselves right now since chapter 8 is in general about solving right triangles, right? So the new thing here now is that we're a little bit stuck in solving for A or for B. But the good thing is that we know all of our side lengths, and our side length ratios are described by our trig functions. So it seems like there should be lots of different statements that we could set up here. By the way, let me write my c equals square root of 13 here. Lots and lots and lots of different statements I could set up here to help myself out with this. All right, so I'm going to do a couple of these right here. So looking at our triangle, here's some things that I'm seeing. One thing I could do, I'm going to make a bunch of statements down here at the bottom, is I could recognize that A and B are my cleanest known values, right? C is a little bit gross right there, square root of 13. Relative to angle A, I'm noticing that lowercase a and lowercase b are opposite and adjacent. So maybe I could make this statement like tangent of A is 2 over 3. From here, I could then go ahead and solve for A by using an inverse tangent function. And whatever I get out from my calculator is going to be the angle that we were interested in. Notice that we could have done this a different way. Maybe instead I would want to say something like tangent of B. Okay, let's stick with, for right now, I'm going to make several statements about A. Maybe instead we're totally fine with the square root of 13 term. Well, maybe I could do something like the sine of A. What's the sine of A equal to in this triangle right here? Sine is opposite over hypotenuse, so that should be 2 over root 13. And therefore, we should be able to make the statement that A is sine inverse of 2 over root 13. Or maybe we could do something like the cosine of A. Cosine of A in this case, adjacent over hypotenuse, is 3 over root 13. And therefore, A should be cosine inverse of 3 over root 13, right? That's 3 different equations that I've come up with, all 3 of which would have been good right there. You definitely only need to do one of them. I'm just trying to show you there's so many different trig statements I could set up, and as long as I can do a single inverse trig operation, then I'm going to be able to find A. Right? So I'm going to say so Another thing to point out here is that these were just my statements about angle A, and they were only the statements using our primary three trig functions. I could come up with three more statements about angle A with secant, cosecant, cotangent, and then we could come up with 6 different statements also associated with B. There's literally 12 different trig equations I could set up, and I only need one of them to either solve for A or B with an inverse trig function, and then use A plus B equals 90 to get the other angle that we're missing out there. So you literally have 12 different options of an equation that you could set up relative to this triangle to help you solve for a missing angle. Once you know one of the 2 missing angles, you can easily find the other by subtracting it from 90. So let's just kind of go to our calculator here and just do one of these guys. These all are going to give A equal to, and again, we can pop over to Desmos here, and in Desmos over here, I know I've just got my scrunch screen over here, shouldn't really matter. Let's get rid of this stuff here. We are interested in things like tangent inverse of 2 over 3. Now, you should notice it's giving us this really, really small decimal value right here, 0.5888. That's because we're in radian mode. If we're thinking in terms of degrees, then we should go ahead and multiply this guy by our 180 over pi to get a, no, is that not? Okay, there we go. To get an angle measure right there. So that was one of the ones that we came up with. We also came up with sine inverse of 2 over square root of 13. Notice there's that same radian measurement that you just saw. If we multiply by 180 over pi, then we're going to get that same thing right there. The other one that we set up was cosine inverse of 3 over square root of 13. Same radian measurement. I multiply this guy by 180 over pi, and boom. So it looks like all 3 of those were equivalent to each other, the 3 different inverse trig equation statements that we set up. All of them gave us 33.69 degrees. That very nicely rounded to 2 decimal places, so I'll just go to 2 on that one right there. So 33.69 is what we got for A. And so that tells me that A plus B equals 90 gives 33.69 plus B equals 90. And all I got to do is subtract 33.69 from both sides, and that's going to tell me that B is going to be, what, 56.31 degrees, right? 80, 89, 90. Yeah, okay. I think I got that guy right there. 56.31 degrees. So boom, there we go. So notice that this is our one new topic because it wasn't until chapter 7 that we got inverse trig functions right here. So the reason why we couldn't quite solve this one back in chapter 6, although I inadvertently even assigned one of these on the My Open Math homework, is because technically these depend on our use of inverse trig functions, which we didn't cover until section 7.1. So this is sort of like our new idea for the day, is that if you only know side lengths and you don't really know any of your angles aside from the 90-degree angle, then we have to use inverse trig functions to help us solve for one of the missing angles. And if we knew one of our missing angles, we very easily get the other by just doing a little bit of subtraction right there. So it looks like we have solved this triangle because I know angles A and B, and I knew all 3 of my side lengths here. So what was this? 33.69 was A. And B was our 56.31 degrees right there. So honestly, my biggest word of warning here is remember that Desmos is always in radian mode. It's very typical for us to discuss triangle angles with degrees instead of with radians. I feel like it's most common to talk unit circle stuff in terms of radians and to talk triangles in terms of degrees. So if you are using Desmos as your calculator, as I often do, you have to include all of those conversions in and out of degrees if that is the unit of measurement that you're using here, all right? So again, you have a ton of choices in a lot of these problems here. You just need to come up with one of the statements that's going to get you there. Sometimes if I'm a little not confident in what I'm doing, I will come up with a second statement and just convince myself I'm getting the same answer so that I feel good about the math that I did there. Now, that was our 2 side lengths are known situation. So what's our 3 side lengths are known? I'm not even going to do one. This is exactly the same. Notice our very, very first step here is to say, oh, we know 2 side lengths. What was the very first thing we did? Was we solved for the third. By doing the 3 side lengths example is this problem, but easier because you've already been given all three side lengths right there. So when I see, if you know two side lengths, you basically know three because the Pythagorean theorem easily just gets you the third one right there. So there's nothing new in this example that we didn't just see in the previous example right here. So I'm not even going to do an example right here. If you know all three side lengths, you have even less work to do. You've just got to set up one trig statement here, take one inverse trig function to get one of your angles, do a little subtraction and get your other angle, and you're done. You have less work to do in the three side length scenario versus the two side length scenario. So what's most typical to be given to you for a right triangle is either one side length and one angle, or two side lengths. These are the common situations to arrive at for solving a right triangle. If you have zero side lengths, you can't do it. If you have three side lengths, that's you being given more information than you actually needed because you could have done it with just two side lengths. So often that's not really the case that you know all that stuff right there. So these are really our two essential cases for the right triangle solving is one side length and one angle, or two side lengths. Once we go to talk about sections 8.2 and 8.3 next week, it's going to be really, really important that we identify not only how many angles and how many sides do we know, but in what order are they around the triangle here. For example, in this guy, we knew 40 and adjacent to it we knew 2. That would be a little bit different than if we knew 40 here and a 2 on the opposite side over here. So when we talk about our non-right triangles next week, we're not only going to want to identify how many sides, how many angles, but in what order are they known. Is it angle, side, side? Is it angle, side, angle? Is it angle, angle, side? What's the order in which we know information about the triangle? That'll be relevant next week in that section out there. So that's kind of all we really have for this one here. Let's take a look at this in action with an application example, and we'll go ahead and we'll call it a day. It's a much simpler, shorter section right here. So this is a really good example. This is a really practical use for this, is talking about building right triangles to measure distances based on only a few distances being known. So a lighthouse is sitting up on a hill. The hill is 245 feet above sea level, and the lighthouse itself is 117 feet tall. If we add together those two number of feet, we'll get the total height above sea level that the light is on the lighthouse. What I want to know is this. Given that the Earth has a radius of 3,960 miles, I want to know how far away from the lighthouse can it be seen, right? So if you're a ship out on the water, from how many miles from shore will you be able to see that lighthouse's light? Right? So this one is one of those ones where I cannot think about this problem if I don't draw a really good picture for myself. So I'm going to give myself a little more room since I'm going to take up a whole bunch of room with a really good picture here. Hey, that's not the worst circle I've ever drawn, but I need room above it, so I have to try that again right here. Let's try a more modest circle. Hey. Hey, that wasn't bad. Hey, high five for Tony today. All right. So here's the Earth. Here's the center of the Earth. And what we're picturing for ourselves here is that we've got a lighthouse here, right? And the lighthouse is like on a little hill. And then there's the lighthouse sticking out from the hill right here, right? So here's the deal. I'm clearly exaggerating how big the lighthouse is, but that's because I want to be able to actually see some things with the measurements I'm going to be making here. So what I'm thinking to myself is that if you can see this lighthouse, then that means that you are like in this like span of angles right here. Notice that if you're sitting like over here on the Earth, you certainly can't see the lighthouse because technically you'd need to be seeing through the Earth to see it. So the furthest away that you could see the Earth is where this dashed line right here just barely touches the circle right there, but doesn't actually pass through it. And similar on the other side over here. This should be sort of like the span of the Earth that is visible from the lighthouse right here. And again, I'm drawing a very exaggerated drawing right here. That's just to help myself visualize the distances that are relevant to the problem here. So what you know, and this is like your cheating knowledge for this problem that obviously wouldn't be given in some like real life scenario, but we're sitting in trig class here, so we know this. What section are we in? We're in section 8.1, solving right triangles. So my question is, where's the right triangle that we're seeing here? And the right triangle that I'm seeing in this case right here is this right triangle where the viewing angle is perpendicular to the Earth, right? And this is exactly how this is going to work, that our viewing angle is going to sort of be this, it's tangent to the circle. It comes and it touches the circle, but then it keeps on cruising right past it, right? And so what I'm seeing here is there should be some length that looks like this that's going to form for us a right triangle. So let's identify that this is a right triangle that I think that I'm interested in right here. So what I'm going to do is I'm going to sort of copy this right triangle. I'm going to kind of pull it out of here, all right? So here's what I'm seeing. I'm going to draw this a little bit different. I'm just going to put this right triangle on its side right here. So this looks like my radius of the Earth right here. This leg that's right here, and therefore this is my radius of the Earth right here. This is my 3960 miles right there. This is my R, my radius right there. This angle right here seems to be the angle of the Earth that we're traversing if we are able to see the ship, right? Notice that this hypotenuse of the right triangle right here is a little bit longer than the radius of the Earth. It's the radius of the Earth plus the height of the hill plus the light of the watchtower, or the lighthouse right there. So I'm thinking that this angle right here, this is, an important thing to maybe observe is that there's the curvature of the Earth is this dashed line right there. So it seems to me like this length right here is sort of broken up into chunks, right? This is the radius of the Earth. And this right here, and what do we get? 245 feet plus 117 feet is going to be 362 feet. This is the height off of sea level that the lighthouse is, right? So I think we can agree that this hypotenuse length of this triangle is the radius of the Earth, right there, 3,960 miles, plus an additional 362 feet. Now, this is one of my problems right now is it looks like we're like mixing and matching units, so that's not really good for me here. So let's go ahead and convert this guy here. So what is it that I really want to know? 362 feet. Let's go ahead and multiply this by, what is it, 5,280 feet in a mile. So I cancel feet with feet, and 362 over 5280. 362 over 5280. And Desmos, my calculator is telling me 0.06856. So that's how many miles the lighthouse is above sea level. Not very many because it's only a couple hundred feet right there, right? 0.06856. Just making sure I wrote down my numbers correctly right there. So here's kind of what I'm seeing. It seems like our triangle of interest, this guy right here, has a length of 3960 here. That's the radius. The hypotenuse is the radius plus the lighthouse height, so it's going to be 3960.08, or sorry, I started drawing my numbers wrong right there. 0.06856. Because it's got that little bit of additional height from the lighthouse right there. And this is the angle through which we have, that we've swept out in our viewing angle right there. Now, here's a really important thing about this is this. What we're not necessarily interested in is what this dashed line distance is right here, which by the way, is I've sort of swapped which line is my dashed line. Here, this dashed line is the leg. Here, the solid line is the leg. Here, the curve is solid. Here, the curve is dashed right there. But what I'm really thinking is if we're measuring distance on Earth, it's really this curvature distance, right? You don't like literally say your distance like through the air that you're going. If you're traveling on the Earth, then yeah, you're traveling on a sphere and we're referencing the distance around the curvature of the Earth. So it really feels to me like we want this arc length. I'm going to put an obnoxious arrow in here indicating that guy right there. That's really what we're interested in. So what is our arc length formula? Let's remember our arc length formula is S equals R theta. Where S is arc length, R is radius, and we've got that. And theta, very importantly, is the angle in radians. So it seems like if we can just find what this theta is going to be, then we know all the information that we need to make an arc length computation right here. So we have come up with the right triangle that looks like this. Remember my decimals here. 0.6856. So my question to you is, what should we do? I mean, should I find this leg? Oh, these sneezes are killing me. I don't think I need to find this leg. This leg isn't any of the information that I care about. Technically, I'm capable of solving for this leg, not meaningful to me. What I want is this angle right here. Relative to this angle right here, it looks like 3960 is adjacent to this angle, and it seems like our decimal value is the hypotenuse. So this is adjacent, this is hypotenuse. And our question is, what trig function deals with adjacent and hypotenuse? That is cosine. So I'm thinking to myself, my cosine of theta should be equal to, cosine is adjacent over hypotenuse, it should be 3960 over 3960.06856, right? Therefore, theta should just be the cosine inverse of that fraction. Now, I'm not expecting this to be a very big number. You should notice that this number is really, really, really close to 1. And when does cosine get an angle very, very close to 1? When our angle is near 0, right? If our angle is 0, cosine of 0 is 1. All right, that's like cosine of our angle. This number is really close to 1. So we're getting an angle that's going to be really close to 0 right here. And that makes sense because we're expecting just a regular old lighthouse. It's not like we're expecting it to see like a quarter of the earth or anything. Like we're expecting it to be able to see a very tiny sliver of the earth. So having a really small angle here does make a bunch of sense to me. So I'm going to pop over to Desmos now and do this calculation. I'm knowing that Desmos is always giving me radians as my outputs, and that's perfect for me here because I need radians for my for the formula that we're about to use. So I'm going to do my cosine inverse of 3960 divided by 3960.06856. And as expected, we're getting a really, really, really small measurement here because this isn't taking up very much angle. If you want to see how many degrees this is, we could multiply by 180 and divide by pi. So it looks like about 1/3 of a degree, 0.33 degrees, about 1/3 of 1 degree is what span of the Earth can view this lighthouse from wherever you're at if you're out on the water out there. I think that's believable. 1/3 of 1 degree of the span of the Earth. I'm into that. It's always hard for me to interpret my radian measurements. I always feel better interpreting in terms of degrees, but I know that I need radians for our arc length formula, so that's what I want right there. Desmos always does radian stuff here. So back in Word, we can state our result right here, 0.00588. And I'm going to keep just a whole mess of decimals right there. The smaller a number is, the more meaningful it is when you round. And so when I see tiny numbers like this, I get real nervous about over rounding. So whatever, just keep a couple extra decimals here. So what is the total distance? Our viewing distance is S, which we compute as R times theta. So S is going to be 3960, the radius of the Earth in miles, times the angle that is swept out in radians. That's our 0.00588 4, 3, 6, 6. And honestly, I'm really just going to go do this in Desmos, and not I'm just going to keep 100% of the decimals over there. So all I've got to do is multiply my cosine inverse expression here. Oh, I just didn't know, that was dumb. I just accidentally clicked the X right there. Cosine inverse of 3960 over 3960.06856. There we go, we're back. Now I can multiply this by 3960, the radius of the Earth. And what we're seeing here is we're getting about 23.3 miles right here. This is our total viewing distance, because this is a mile measurement right there. So it looks like we're going to get our 23.30 miles is our final answer here. Sorry, 23.30, yeah. All right, if you're any further away from this than the lighthouse, then the lighthouse is going to be beyond the horizon from your perspective, right? And so this is one of those things where as you're coming towards shore, you're seeing like sort of the tops of buildings on downwards. And by the way, this is kind of how we've known that the Earth isn't flat. Like the whole thing about people believing that the Earth used to believe that the Earth is flat. That's not really a real thing. We've pretty much known the Earth is round for a crazy long time, because all you've got to do is see a ship coming into shore, and you'll notice that you always see the very tops of the masts of the ship first, and then more of the mast on down to the bottom of the boat right there. The only way that would ever happen is if you are sort of, in a sense, coming around a corner right there, coming around the curvature of the Earth. If Earth was flat, then you'd always be able to see the whole ship at once, just as a point on the horizon right there, and that's just not how things work, right? And so people have been watching ships come to shore for like thousands of years before the poor academic rumor that people used to think that the Earth was flat. There was really that wasn't really a thing. For the most part, people that were able to make basic observations like seeing ship masts before ship bodies, we've known that the Earth was round for a really long time because of exactly this reason right here. So this is a really cool problem here. Obviously, pretty practical, being able to measure distances on the Earth's curvature rather than just lengths of triangles. So notice that this problem here was sort of about solving a triangle, but is really saying, given one length and another length that's a little bit longer, can you find the relevant angle so that we can use the angle in an arc length formula? So this is sort of like solving a triangle. We didn't solve the whole thing, but we did compute an angle given two known side lengths. It did require the use of an inverse trig function, which is why this belongs after section 7.1, and we couldn't quite have done this problem in chapter 6. So here we go. So I'm sure you're going to see some application problems that look vaguely like this in your homework out there. So now you've seen an example that looks like this guy. So as promised, section 8.1, quite a bit easier, I think, than section 7.8. I'm going to see you guys next week for 8.2 and 8.3. They're very, very closely related to one another, the law of sines and the law of cosines. It's going to be a little bit tougher than this here today, but not by a ton. It's basically going to be more of this, except our triangles won't include a 90-degree angle in them anymore. And so what that really means to us is we don't necessarily get our same trig ratios. Remember that every definition that we've given of sine, cosine, tangent, all that stuff, those are all dependent on a right triangle. And so as we depart from right triangles, we need to get a little bit more careful as to how we use our trig functions. You should notice that if we don't have a 90-degree angle in our triangle anymore, then how do you know what's opposite, adjacent, and hypotenuse anymore? Or I guess hypotenuse, like what hypotenuse is opposite of the 90-degree angle. Once we don't have a 90-degree angle anymore, we don't have a hypotenuse anymore. Things are going to get a little bit not as super straightforward as they've been with defining our trig functions relative to those triangles. But that's next week. So, and again, I don't, these aren't too terribly difficult. They're a little bit more difficult than today, but I think today was pretty easy. So I will see you guys next week for 8.2 and 8.3, the law of sines and law of cosines. And that's all that we're covering in chapter 8. So in week 12, we'll be starting with chapter 9, following that up. Have a good one, everybody. I will see you then.